Hello viewers, welcome back to this series of lectures on quantum mechanics. In today's session, I'll talk to you about hydrogen molecule ion. This is the first molecular system we are going to take up. The session is planned as follows. To begin with, we will try to introduce ourselves to molecular systems. Thereafter, we will define hydrogen molecule ion as a quantum mechanical system. Thereafter, we will typically, as we have been doing all these times, we will try to formulate the Schrodinger wave equation for hydrogen molecule ion so that we can proceed further and try to get suitable wave functions for that. And in this process, we will try to not exactly separate, but state the Schrodinger wave equation for electronic motion and also for the nuclear motion. And thereafter, we will realize that in order to move further, we need to introduce some kind of approximation methods. And in this context, we will try to talk a little about the variation theorem, which we are going to use in subsequent sessions to solve the hydrogen molecule ion problem. And towards the end, we will try to sum up what we do today. Let's move further. I think before moving further to introducing ourselves to molecular systems, it's time that we take stock of what we have done so far in this course. If you really ask me, this course can be looked into having three components. The first one is why of quantum mechanics, second, what of quantum mechanics or wave mechanics, and third, how of it. In the first domain, the first aspect, what we did was we started by talking about what is classical mechanics, how is it successful in talking about or describing the behavior of macroscopic objects, and then thereafter we confronted classical mechanics with certain experimental observations, and in the process we established that classical mechanics is inadequate in explaining the experimental observations in number of cases. This led to the proposition of the concept of quantization by Max Planck, and which subsequently led to formalism of wave mechanics by Erwin Schrodinger. So this was about basically it established that we need some kind of a theory which can describe the behavior of macroscopic systems, and that was translated into the wave mechanics by Erwin Schrodinger. And in that context, we saw that wave mechanics basically is a formalism, a set of rules by which we play the game, and whereby we try to describe the behavior of quantum mechanical systems. Thereafter, we came down to the how of it. In the context of how of it, we started by talking about the simple model systems like particle in one-dimension box or particle in three-dimension box. So we acquainted ourselves with how does quantum mechanics work or how does wave mechanics work. Thereafter, we graduated ourselves to the first atomic system, that is hydrogen atom, on which we spent a lot of time to understand, and we also realized in the process that how difficult does it become the moment it becomes a little real kind of a system which at least has got two particles. Today is time that we are graduating further. We are trying to now move on to the molecular systems, which are having more than two particles. And in this context, we will start with the simplest possible system, that is hydrogen molecule ion. So that's where we are. So we will spend some time now, so a few sessions we will talk about. So in the process, we will lay foundations on how do we give a quantum mechanical description of chemical bonding. So that's a broad objective we have before us for the next few sessions. Okay, now let's get formally into the session today. That is, let's see how do we introduce, what are the molecular systems we are referring to. Typically, if you ask, a molecule may be defined as a chemically bonded system of atoms that exist as discrete entities. So two atoms come together, they form a molecule, 2, 3 or any number, at least 2 are to be there. So, but the requirement is that the entity must be discrete on its own. And hydrogen molecule ion is the simplest possible molecule, because it's a molecule which contains two nuclei and only one single electron. The simplest possible molecule we can think of, and which exists independently. Then another thing which probably we have to make a statement here is that this hydrogen molecule ion has a very pivotal role in our understanding of molecular structure, because it plays the same role as played by hydrogen atom in understanding the atomic structure, because we learnt about structure of hydrogen atom, and then that could be extrapolated to multi-electron atoms. We didn't do much in this course, but we all are aware of it from our earlier knowledge. Now similarly, this hydrogen molecule ion, the simplest possible molecular system, is going to lay foundations for our understanding the molecular structure. We talk about hydrogen molecule and other molecules, diatomic molecules and things like that. It typically is difficult to solve Schrodinger wave equation to get the wave functions. So in the process, probably, as I mentioned earlier too, that we need to use some kind of approximations. You will appreciate here, we were comfortable when we talked about only single particle, confined to a one-dimensional box or a three-dimensional box. The moment we came down to two particle problems, say hydrogen atom, we were in problems. So we had to do a lot of strategies to be followed, and some kind of manipulations we had to get through, so that we can get some solution out of it. We did get solution in fact. But the moment we move further to a three particle problem or multiple particle problem, then things are going to get more and more difficult for us. So we need to introduce some kind of approximations. So that's the kind of molecular systems we are going to handle now on. Now how do we go about is that there are basically as regards quantum mechanical approaches to molecular structure, there are two broad ways of looking at molecules quantum mechanically speaking. The first one happens to be the valence bond theory. What valence bond theory is, according to valence bond theory, the bond formation is visualized as localized interaction between two atomic orbitals belonging to the constituent atoms. That means suppose I got two atoms, atom A, atom B, the two are going to combine together to form a molecule AB. So essentially valence bond theory says that we have got interaction between these atomic orbitals, which is very localized kind of an interaction. We will elaborate on it as we proceed much later. And the second approach, which is called as a molecular orbital theory, which we are going to focus primarily, it has a very different perspective. According to molecular orbital theory, the bond formation, the formation of a molecule from two atoms, can be seen as there are delocalized molecular orbitals, because in case of atoms, you have an atom, there is a nucleus there, there is an atomic orbital around that. In case of molecule, it visualizes that there are molecular orbitals which are spread over the whole molecule. We will talk more about it as we proceed. The basic difference here is, in one case we are talking about a localized interaction, localized bonding, that is valence bond theory, whereas in case of MO theory or molecular orbital theory, we are thinking about delocalized kind of orbitals there. So this is the starting point for us. We will elaborate more as we proceed further. Now let us get on to defining what is my hydrogen molecule ion. So if you look at hydrogen molecule ion, it is a very simple system. There are two atoms, I call it as nucleus A and nucleus B, and there is a single electron. So if you really ask, because this is a generalized representation of that, but this happens to be a proton H plus, this is another proton, and this is one electron there. So it is H2 plus. So this is a hydrogen nucleus, another hydrogen nucleus, and there is a single electron there. So that is what system I am dealing with. So essentially this is the simplest molecular system that consists of two nuclei and a single electron. In this case, there are two attractive interactions possible there, because this electron will experience attractive interaction with this nucleus, say nucleus A, and also with nucleus B. So that is a kind of the two possible attractive influences are there, and between the two nuclei I am expecting a repulsive interaction there. Okay. So there are two attractive interactions and there is one repulsive interaction between two nuclei which are separated by a distance r there. Another thing we have to take note of here is that the internuclear distances are represented in terms of capital R. I am just putting it very grossly, and the electron nucleus distance are given in terms of small r. So there are a variety of ways of doing that, but that is what we are going to follow here. Okay, so that is the kind of system I am going to deal with. If that is my system, then as we have been doing all these times, for any quantum mechanical system to be handled, what we have to do is, the first and foremost requirement is we must be able to write down the Schrodinger wave equation for the system, and that happens to be, simply put, H psi is equal to E psi, where H happens to be my Hamiltonian. So, in a way, formulating Schrodinger wave equation amounts to formulating the Hamiltonian operator for the given system. And we also know that Hamiltonian operator is nothing but sum of two operators. One is my kinetic energy operator and potential energy operator, because Hamiltonian is an operator for total energy. So, essentially we need to design a suitable Hamiltonian for our system in question. Okay. So, how do we do that? How do we do that is, we start with the kinetic energy part of it. We will not get into details of that, because we have learnt, we have done so many times now. So, now we know how to just straight away write down the Hamiltonian. As regards kinetic energy part, we see that there is 3 particles are there. So, the nucleus A has some kinetic energy, nucleus B will have kinetic energy, electron also will have kinetic energy there. So, there are 3 contributors to the kinetic energy of the system, and that is the system I was trying to put back over here. So, we can straight away put the kinetic energy operator for the nucleus A as minus h cross square by 2 mp, where mp is the mass of nucleus A, which basically is nothing but my proton. So, it is mass of proton here, and del A square, where del A is a Laplacian operator for the nucleus A here. Now, this kinetic energy operator is basically, I am trying to just kind of recall from particle in 3-dimensional box. So, it is just like that, there is one particle. So, it is moving in 3 dimension. So, what is the kinetic energy operator for that? That is this one. Similarly, for nucleus B, there is a similar energy operator there, kinetic energy operator, and the kinetic energy of electron can be given as minus h cross square by 2 me. So, that is the difference here. You talk about the mass of electron here, and also del E, because del E will depend on the coordinates of electron, whereas these two were dependent on the coordinates of the nuclei, nucleus A and nucleus B. So, that is my kinetic energy operator. Similarly, we can work into the potential energy operator. So, we know that the potential energy consists of 3 components. First is attractive influence between nucleus A and electron, then attraction between nucleus B and electron, and then repulsion between nucleus A and nucleus B. So, these 3 terms can be translated into the following expression, that is, V will be equal to minus E square by 4 pi epsilon naught R A, and similarly this is for the first term here, that means attraction between electron and nucleus A, this is electron and nucleus B, and this is the repulsion between 2 nuclei A and nucleus B. So, that is my potential energy put together. So, I get Hamiltonian to be this large expression. There are 6 terms in that, 3 for the kinetic energy part, 3 for the potential energy part. If that is my Hamiltonian, my Schrodinger wave equation, the which I wanted to design, happens to be the following. So, so I have got, this is my Hamiltonian there, and this is my psi to be equal to E psi, and then this psi, the wave function, I have deliberately not put the dependent variables over there. So, psi will depend on small r's and capital R's, where small r's are the ones which are describing the location or the coordinates of electrons, and the capital R, as I mentioned earlier, represents the coordinates of the nuclei. So, that is the Schrodinger wave equation I have to handle. Okay. So, what is my next step? The next step is, before I proceed, let me just try to see what kind of Schrodinger wave equation I have got. I find that this equation happens to be a little complicated. Why so? Let us see. There are a number of issues with it. The first one is, this is a 3-particle problem. There are 2 nuclei and 1 electron. As I mentioned earlier also, when I had particle in 1-dimensional box or 3-dimensional box, a single particle, we could manage. In 1-dimensional box it is easier, 3-dimensional box we had to do some manipulation there, and when we came down to 2-particle problem, it became difficult. Now, it is 3-particle problem, it gets even more difficult, and if we go for larger atoms or larger molecules, it will be still more difficult. So, that is the first kind of aspect of the complication of this equation. Second one is, the electronic behavior of the electron in this molecule is influenced by the nuclear behavior. That is fair enough, because in this case what we have is, there are 2 nuclei, the 1 electron there. So, in case of an atom, we had 1 nucleus, 1 electron. So, if you hold it here, so we could work out how does the electron behave there. Now, the electron behavior is influenced by where are 2 nuclei, are they close by, are they farther apart from each other, or what kind of interactions are they having, what is the nature of the nuclei. So, all those are going to determine by the electronic behavior in the system. Another thing which is very pertinent here is that is the internuclear distance may change. That is very important here. What happens is, as it goes, there is no molecule which is stationary. Okay, that means all molecules undergo at least the vibrational motion. Suppose I got a molecule like this, A, B, and if it is executing a vibrational motion, so it is that's the simplest possible vibrational motion I can think of. When it is executing vibrational motion, essentially what's happening is this is my kind of equilibrium internuclear distance. It will increase, come back same, decrease, and so on and so forth. So, since the internuclear distance is changing, so that is going to complicate matters, because what kind of internuclear distance I am going to consider to solve the equation. So, we will come to that as we move a little further. And another thing which I mentioned earlier too, that this equation cannot be solved exactly in very easily speaking, but if you indulge into this, probably we can get solutions which will be which will need a lot of effort to achieve that, and maybe the kind of results we get may not be what we are worth the effort over there. Okay, let's move and see that how do we get over this. To get over this, we need to make some kind of assumptions, and maybe we have to resort to some kind of approximations. Let's see what are these assumptions and approximations. The first, very crucial, particularly for all molecular systems, a very crucial approximation is what is called as a BornOppenheimer approximation. Now, this is, as mentioned earlier, is very crucial. So, what is the basis of this approximation? The basis is that we know the nuclei are much heavier as compared to the electrons. So, the mass of nucleus or mass of a proton is about 1836 times that of the electron. So, it is much bulkier. So, what does it mean? It means that the velocity of nuclei is far less as compared to that of the electrons. Electrons are moving much faster as compared to that of the nuclei. So, that is very crucial observation, and that is what was considered by Born and Oppenheimer to suggest an approximation. And that approximation happens to be that as a first step to deal with molecular systems, what we can do is we can assume that the nuclei are not moving and the electrons are moving in the field created by the stationary nuclei. So, in our context, we have got two nuclei, nucleus A, nucleus B, or proton A, proton B, and the one electron. Now, suppose at a given instant these two protons are here. So, when they are here at this distance, the so called bond distance or bond length, so in that situation, what kind of influence do they in what way can they do they influence the electron? So, that has to be considered. So, that is the way we go about it. So, that is one of the most fundamental and pertinent approximation we have to apply in the context of molecular systems. Okay. Now, what are the implications of this? This approximation implies that the overall wave function can be considered to be product of two parts, a nuclear part and an electronic wave function. So, there are two wave functions. That means my total wave function will be product of psi nuclear and into psi electronic. Okay. And then another very significant implication of this approximation is that the total Hamiltonian, that means which we just seen, there are 6 terms in that probably can be broken into two small parts, one for the nucleus, the other nuclei, and the other for the electron. So, that is going to make life easy for us as you proceed further. As a consequence of these two implications, the Schrodinger wave equation can be separated into two parts. So, one for the nuclear part, one for the electronic motion, and that makes easy as you proceed. Now, what is this Schrodinger equation for the electronic motion? The Schrodinger wave equation for electronic motion for our system, that is hydrogen molecular ion, can be given as shown over here. That is, this is basically my h cross square by 2 m E del E square and so on and so forth. That's a thing we because this talks about the kinetic energy of electron, and these terms are regarding the potential energy part of it. That's my psi electronic and E, or you can put it as E electronic and psi electronic. Now, the encircled term here, the term which I put into this oval shaped here things here, that represents the potential energy due to the two stationary nuclei separated by distance r. That has to be understood, because this follows straightway from our BornOppenheimer approximation, because we just said the nuclei are in motion, and also if a molecule is executing vibrational motion, the internuclear distance changes. So, what this equation tells us is that as per the approximation, we freeze our nuclei for a moment. So, for that particular internuclear distance called as capital R, what is the influence of that? That is that's a potential energy because of those nuclei has to be considered over here. This is simple terms. These two are very simple terms. They basically refer to the attractive influence of the nuclei on the electron. So, that is very simple, but this is about the nuclear part of it. So, this is my electronic equation. This is what we need to solve to understand our molecular system there, that is hydrogen molecule ion. Now, the nuclei are considered to be stationary, that is the bottom line. Okay. Now, as regards the nuclear motion, that is a kind of expression we have. So, these two terms are about the kinetic energy of the nuclei, and the third term which is enclosed here basically represents the electronic potential energy obtained by solving the electronic Schrodinger wave equation. This needs to be understood. What it means is, that is, I fix the value of R, capital R, that means I freeze my nuclei at a certain distance and then try to solve the electronic wave equation. So, when I solve that, I get an outcome as E electronic. So, that E electronic now serves as a potential energy term in this nuclear expression. So, that is now I have got to solve. So, this can be solved only once I have got E electronic from there. So, that comes, this E electronic term or E electronic as a function of R will come from solving the electronic the Schrodinger wave equation for electronic motion. Okay. So, it means the nuclei are considered to be under the influence of an average electronic field. Okay. Let us see what is the strategy from here on. What do we do is that we need to solve the electronic Schrodinger wave equation. We start by solving it for a given value of R. That means, we take certain value of R, and for that value of R, we try to work out, we try to estimate what is the internuclear repulsion term. Okay. So, that is the energy of that. So, that we incorporate into the equation and solve that electronic Schrodinger wave equation. Then we repeat the same process for different values of R. That means, suppose I take this value of R, I find out what is the electronic energy, increase it, increase it, increase it, come back, decrease, compress, and I continue doing that. Or maybe another way could be, I take that to be very, very far and then see what is the potential energy. I bring them closer and closer and closer and then see what do I get. So, I go on changing the value of R, the internuclear distance, and see how does it change the energy of the system. And that actually gives me a very familiar kind of a curve, what we know it as the potential energy curve. We will talk about it move further. Then this value of ER, because this actually gives me how does E change or E electronic change as a function of R. So, this is substituted into the nuclear equation or the equation for nuclear motion, and that is solved thereafter. So, that is the kind of strategy we have, and the core of it, all this strategy is the first thing, that is, we need to solve the electronic Schrodinger wave equation. How do we do that? How do we do that is, to solve the Schrodinger wave equation, we need to resort to some kind of approximation methods. It is different from the BornOppenheimer approximation we talked about earlier. That is, we are treating nuclei as stationary. But now, we are talking about approximation methods in terms of how do we operate, how do we work on the equation. So, that is a different kind of approximation we are talking about. And to this extent, there are two approaches. One is called as a perturbation method or perturbation theorem or perturbation process, whatever you want to call it as. So, in this case, what happens is, suppose you got a large Hamiltonian, and because that Hamiltonian H psi E psi, that is the equation we have to solve. With this Hamiltonian as such, we maybe are not in a position to solve the equation. So, what we do is, we keep aside a little part of the Hamiltonian and take only that portion which probably can be solved. So, that is my starting point, and with that we try to work out what is the wave function. Then thereafter, having done that, we incorporate this something which we left out, a part of the Hamiltonian, as a perturbation, and then see how does the system change. So that is a kind of process it undergoes. That is perturbation method. The second method which we are going to follow is called as a variation method. In this case, what we do is we take the Hamiltonian as it is, but we do not solve the equation to get the wave function. As against that, we make a trial wave function. We take some wave function using our common sense, and then which we expect may be a suitable, well behaved wave function for the given system. Take that wave function and try to see that with Hamiltonian as designed, what kind of energies do we get, and then compare that energy with the actual energy of the system. And if the wave function happens to be true wave function, the energy will come out to be the true energy. If you have got any other wave function, the trial wave function happens to be different from the true wave function, then energy will come out to be more than the actual ground state energy. So that is a basic premise of variation method. So we take a trial wave function and put a lot of parameters in that, go on playing around with the parameters, and then see what kind of a combination of these parameters gives me the minimum energy. So that is the wave function. That's the way I get my wave function for the given system. So that is my variation method, and that is what we are going to use as we proceed. So just for sake of it, let's state what is variation theorem. The variation theorem states that a well behaved approximate or a trial wave function would give an average or expectation value of the energy equal to or greater than the true ground state energy of that system. That is what I just mentioned. That is, if that is my expectation value postulate. So if I take a trial wave function and take my Hamiltonian as it is come from the system, if I compute the expectation value, it will come out to be equal to E naught or greater than that, equal to when my wave function incidentally or accidentally happens to be the true wave function, I will get E naught. If it is anything else, I must be getting more than E naught. So that is the that's a theorem we make use of here. In the context of our understanding of molecular structure, we are going to primarily focus on two theories. One is valence bond theory and second is molecular orbital theory, more of molecular orbital theory. Essentially these two approaches, VBT and MOT, they use different ways or approaches to design the trial wave function. Both are using variation theorem. The only thing is what kind of trial wave function do I use, that will depend on the basic premise of the theories I am going to make use of. We will talk about it more as we proceed. Now, the molecular orbital theory uses linear combination of atomic orbitals as the basis of generating the molecular orbitals. That is what we are going to follow in our next session. Okay. So you see that both the theories are attempting to answer the same thing, but they have got different approaches to that in terms of what kind of wave function we take it as a trial wave function. Okay. So that is probably where we are going to stop for today, and we will build on this in the next session. And towards the end, let me just sum up, as I promised earlier, what we have done so far. What we have done in this session is we took a stock of what we have done so far. Thereafter, we introduced the quantum mechanical approach to molecular systems, that is what kind of two theories we are talking about, VBT and MOT. Then we defined our system for today, that is hydrogen molecule ion. Thereafter, we formulated the Schrodinger wave equation and explained the rationale, that is why of it, and what is significance, what is the outcome or implication of that kind of an approximation when you apply to the molecular systems. And then we stated the Schrodinger wave equations for the electronic motion and for the nuclear motion, and then thereafter we briefly touched upon the approximation methods used for solving such kind of an equations. I think with that we will try to stop for today. In next session we will try to use variation theorem and see what kind of wave functions do we get for our hydrogen molecule ion. Thank you.